All right, in this video, we're going to talk about section 2.6. And in 2.6, we're going to be dealing with continuity. And this will pretty much wrap up chapter 2 in my course. So pretty much in this section, we're going to be talking about continuity. We're going to be using the continuity checklist to determine whether the following conditions hold for a function to be continuous. And then we'll look at some of the continuity rules, and then we'll look at polynomials and rational functions where they're continuous, what intervals that they are continuous. Then we'll look at continuity of a composite function at a point, and then we'll look at the intermediate value theorem. So there's some things that we're going to cover in this section. All right, section, the graphs of many functions encountered in this text, no holes, jumps, or breaks. They contain no holes, no jumps, no breaks. For example, if L is equal to some function f of t, and it represents the length of fish t years after it is hatched, then the length of the fish changes gradually as t increases. Okay. Consequently, the graph of L equaling to f of t contains no breaks, as you can see in this illustration on the left side. Here, the time in years, and then the length in inches. So here, that's what the curve looks like. It has no breaks in it. Now, some functions, however, do contain abrupt changes in their values. Consider a parking meter that accepts only quarters, and each quarter buys 15 minutes of parking. Let's say we let C of t be the cost in dollars of parking for t minutes. The graph, which is this right here, of C has breaks at integer multiples of 15 minutes, okay? So it's like 25 cents for 15 minutes, and then it jumps up to 50 cents after 15 minutes, but at least 30, and then greater than 30, but at least 45 is 75 cents, and so on. So there is a jump in that graph. And this, by the way, is called the step function. Okay. All right, now, informally, we can say that a function f is continuous at a if the graph of f does not have a hole or break at a. That is, the graph near a can be drawn without lifting the pencil. Now, if the function is not continuous at a, then a is considered to be a point of discontinuity. Okay. So here's the definition of continuity at a point when we're dealing with limits here. A function f is continuous at a if the limit as x approaches a of f of x is equal to f of a. If f is not continuous at a, then a is a point of discontinuity. Okay. So here, function will be continuous at a if your limit as x approaches a of the function is equivalent to f of a. Otherwise, point A would be considered a point of discontinuity. Now, there's more to this definition than what we see here. If your limit is x approaches a of f of x equal to f of a, that means that f of a and the limit as x approaches a of f of x must both exist and they must be equal. So here we have a checklist for determining whether a function is continuous at some number a. Okay, so here is that continuity checklist here. And it states, in order for f to be continuous at a, the following three conditions must hold. Number one, f of a is defined, meaning that a is in the domain of f. So f of a must be defined. And then number two, the limit as x approaches a of f of x has to exist. And then number 3, the limit as x approaches a of f of x equaling to f of a. Both the limit as x approaches a of f of x must equal to f of a. That means the value of what f is equals to the limit of f at a. They both have to be the same. And all 3 of these must be met in order for a function to be continuous at a. Okay. Now on the next page, it says this: if any term in the continuity checklist fails to hold, if any item in that continuity checklist fails to hold, the function fails to be continuous at a. And from this definition, we see that continuity has an important practical consequence, and it's this: if f is continuous at a, then the limit as x approaches a of f of x equals f of a, and direct substitution may be used to evaluate the limit as x approaches a of f of x. Okay. All right, so now let's look at this first example that we have here. And let me see if I can get all of this on the screen. There we go. Let's say we want to determine the points at which the function f below has discontinuities. For each point, state the conditions in the continuity checklist that are violated. In order for f to be continuous at a, the following 3 conditions must hold. And that's these 3. Number 1, f of a is defined, meaning a is in the domain of f. Number 2, the limit as x approaches a of f of x exists. And number 3, the limit as x approaches a of f of x has to equal f of a. So the value of f equals the limit of f at a. Well, by looking at this graph right here, I can see some issues here. Take a look at 2. There's a vertical dotted line there at x equals 2. That's what we call a vertical asymptote. So we know with a vertical asymptote, it's not going to be defined. The function will not be defined at that vertical asymptote. And here it's not going to be defined at x is equal to 2. And also, if you look someplace else, you're going to see an empty circle solely at x equals 4. So at x equals 2 and at x equals 4, the graph of f of x is not defined at x equals 2 and x equals 4. That means here, 2 is not in the domain of this function. Neither is 4 in that domain. So at x equals 2 and x equals 4, the function is not defined. All right, and also something else. At 2 and at 3, the limit does not exist. And I will explain why the limit at 2 and at 3 does not exist. Okay. As you can see here, at 2 is a vertical asymptote. So we know that it's not going to exist there. Now at 3, we got 2 different values there. When you take the limit as x approaches 3 from the left, this graph is getting closer and closer, or the y value is getting closer and closer to 2, as you're going to see here. And then as we let x approach 3 from the right, and this is 3 right here, notice that it's getting closer and closer to 1. From the left, it's approaching 1 value. from the right is approaching another different value. So here we know the limit there at 3 does not exist. So here the limit as x approaches 2 of the function f of x, it does not exist. At x equals 3 and at x is equal to 2. Okay. At 3 and at 2, the limit does not exist. And for that third requirement where the limit is x approaches a of f of x has to equal to f of a, well, I know at, well, this will not meet that requirement. The limit as x approaches a of f of x will not be equal to f of a. And that's for x is equal to 2 and x equals 3. And we might as well include x is equal to 4 as well. Okay. Okay. It's not going to, the limit of f of x will not equal f of a at 2 because of the fact that at 2 is undefined. And at 3, here you got the limit going to the left of 3. So one, it goes to one value from the left, and from the right, its limit is another value. And at 4 does not exist. So the limit as x approaches a of f of x does not equal to f of a at 2, 3, and 4. Okay. All right, take a look at example 2 on the next page. Example 2. Let's say I want to determine whether the following function is continuous at a using a continuity checklist to justify the answer. All right, so first of all, we need to check to see if f of a is defined, meaning that a has to be in the domain of this function f of x equal to the square root of x minus 7. And here our a that we're dealing with is 1. So let's start off by doing this. Let's do f of 1 first. Okay, because the first rule is that f of a has to be defined. So that means f of 1 must be defined for this function. Well, if I replace the x with 1, I'll have the square root of 1 minus 7. And 1 minus 7 would be negative 6. Well, I can't take the square root of negative 6 to get a real number from it. So at 1, f of 1 is undefined. F of 1 is undefined. And then the limit as x approaches 1 of that function f of x. Well, this is only defined for values that are bigger than or equal to 7. Because if you take what's underneath that radical, which is x minus 7, set it to be greater than 0, greater than or equal to 0, that means any x value greater than or equal to 7 will work for that function. But when you take the limit as x approaches 1 of f of x, that limit does not exist. And here I'm using DNE for does not exist. And then finally, the limit as x approaches 1 of f of x will not equal to the limit as x approaches Well, actually, I should say just f of x, because that's the third rule. It does not equal the limit of f of x as x approaches 1 does not equal to f of 1. And basically, if you look at this, since this was undefined, I could stop right here and just say that this function is not continuous at 1, okay? Because if it violates any one of those 3 rules or 3 requirements, then we can say that it's not continuous. So at 1, this function is not continuous. Okay. All right. So that's pretty much dealing with the continuity and using that checklist. All right, next we're going to look at some continuity rules here. And the following theorems make it easier to test various combinations of functions for continuity at a point. Okay, so this is theorem 2.9 dealing with continuity rules here. I just read off what this says here. If f and g are continuous at a, then the following functions are also continuous at a. Assume that c is a constant and n is greater than 0 and that it is an integer. So the sum of f and g, that's the sum of 2 functions. The difference of 2 functions, f minus g. The product of some constant times a function. And also the product of 2 functions, f and g. Also, f divided by g, that's the quotient of 2 functions with the provision that g of a does not equal to 0, and f of x, whatever that is, f of x raised to the nth power. Those functions are continuous at a if f and g are continuous at some value of a. Okay. All right, next we'll look at polynomial and rational functions. Here, a polynomial function is continuous for all x. That's a given right there. So any polynomial function, meaning that if you substitute any x in that polynomial function with a number, you're always going to get an f of x value for it. So a polynomial function will be continuous at all x, meaning the interval will be from negative infinity to infinity. Now for a rational function, that's a function in the form p over q, where p and q are polynomials. It is continuous for all x, for which q of x, which is your denominator, is not equal to 0. So what you have to do there is take your denominator, set that equal to 0, and determine the values of x that would give you a 0 in the denominator. So now let's look at some examples here of just that. All right, let's say we want to determine the intervals on which the following is continuous. In this case here, we got p of x is equal to 2x to the 6th minus 3x to the 5th minus 7. And we want the interval or the intervals on which this function is continuous. Well, notice it's a polynomial function. You're not going to get a 0 anywhere in this denominator. That means any x value that you assign to it, you will always get an f of x value for it. So in interval notation, this function p of x is continuous on for all x, negative infinity to infinity. Okay, because it does say that a polynomial function, which is what we have here, is continuous for all x. Okay, now on the next page. Let's say we want to determine the intervals on which the following function is continuous. Here we got f of x is equal to x squared minus 8x plus 15 divided by x squared minus 9. This time we have a rational function. Here we have a numerator and a denominator, and we got the variable in the denominator. So what we need to do there is take our denominator of x squared minus 9, set that to be equal to 0, because I want to find out what values of x that will give me a 0 in the denominator. And I will exclude those. So it'll be continuous everywhere except those x values. So let's solve for x squared by adding 9 on both sides. So here x squared is equal to positive 9. And then to get x by itself, we're going to take the square root on both sides. And when you do that, you must include that plus or minus symbol. So the square root of x squared is x equaling the plus or minus the square root of 9 would be 3. So here, the values of x that will give me 0 in the denominator will be x equals positive 3 and x equal negative 3. Now, let's say in the homework, they want you to give the interval notation for that. Okay, if this helps, you can draw a number line like I'm about to do right here. Let's say this is 0, negative 3 is here, and 3 is here. Now we know at negative 3 and 3, we're going to have problems. So I put parentheses around the negative 3 and parentheses around the 3. Any x value less than negative 3 would work. Any x value between negative 3 and 3 would work. And any x value greater than 3 would work. So for this function, it is continuous on these intervals from left to right, negative infinity up to negative 3, or from negative 3 to 3, or from 3 on to infinity. Okay. Okay, so that's how we solve that problem. All right, here's one more of these. Here I want to determine the interval on which this function f of x equal to 5 over x squared minus 4 is continuous. So in this case here, we again have a rational function. So that means we need to take our denominator of x squared minus 4, set that to be equal to 0, and find out what values of x that would give me a 0 in the denominator. So to do that, I need to add 4 to both sides. So that means I'm going to have x squared is equal to 4. And to solve for x, since I'm squaring, the opposite would be to take the square root on both sides and include the plus or minus symbol. So that means x is equal to plus or minus 2. So that means at negative 2 and at positive 2, I'm going to get a 0 in the denominator. And of course, let's say this needs to be written in interval notation. Let me draw the number line over here. In this case here, negative 2 is here and positive 2 is here. So we know at negative 2 and at 2, we're going to have zeros in the denominator. So I'm going to use parentheses around those. And any x value less than negative 2 would work. Any x value between -2 and 2 would work, and any x value greater than 2 would work. So this function is continuous on this interval from -2 up to, from negative infinity up to -2, or from -2 to 2, or from 2 on out to infinity. Okay. So that's how we determine the intervals where a function, whether it's a polynomial function or a rational function, is continuous. Okay, now let's look at continuity of a composite function at a point. And it's going to be this. If G is continuous, if G is continuous at a point A and F is continuous at G of A, then the composite function F circle G, that is F circle G, by the way, is continuous at A. Now, we should be familiar with what a composite function is, by the way. So I'll remind you, if you don't know. The composition of F with G of some X, that means this, F of G of X. That's what that means. The inside function is G of X, your outside function is F of X. And basically, when you're given two functions, F and G, and if you want to find the composition of F with G of X, what you do there is take whatever G of X, substitute it for each and every X in F of X. Okay. That's what we mean by composite functions. All right, so now on the next page is the limit of composite functions. So we're going to deal with that. How can we take a limit of a composite function? All right, if G is continuous at A and F is continuous at G of A, this is number one, then the limit as X approaches A of F of G of X would be equal to this, F of the limit as X approaches A of G of X. You'll take the limit as X approaches A of G of X first. Whatever this is, you'll evaluate F of whatever this is by replacing each X with that limiting value. Now, number two, if the limit as X approaches A of G of X is equal to L and F is continuous at L, then the limit as X approaches A of F of G of X would be also this, F of the limit of G of X as X approaches A. All right, so in this case here, let's start with example 6. Let's say I want to find the limit as X approaches 0 of 4x to the 8th minus 6x to the 4th plus 1, and that quantity is to the 37th power. Okay, this is what I'm going to do here. I'm going to identify two things, the f of x and g of x. Now, since we're dealing with, in this case, f of g of x, g of x is the inside function, so what's inside the parentheses here will have to be g of x. And that g of x in this case will be that 4x to the 8th minus 6x to the 4th plus 1. Well, if g of x is this, then that means f of x, this was put in place of x. So that means f of x will have to be x raised to the 37th power. Okay, and this is what we call decomposing functions. Taking a composite function, breaking it into two parts, what f of x is and what g of x is. And you can pretty much check by just substituting the x in the f of x function with that g of x, and you will get this back. All right, so now let's start by taking the limit as x approaches 0 of, well, we know it's going to be f of g of x, but I can apply that rule up here and write that as f of the limit as x approaches 0 of the function g of x. Now to the side, I'm going to do the limit as x approaches 0 of g of x. But g of x is that 4x to the 8th minus 6x to the 4th plus 1. So I'll evaluate the limit as x approaches 0 and replace that g of x with 4x to the 8th minus 6x to the 4th plus 1. And since this is a polynomial function, we can just do direct substitution. So here this would be 4 times 0 to the 8th minus 6 times 0 to the 4th plus 1. Well, guess what? 0 to the 8th is 0 times 4 will be 0. 0 to the 4th is 0 times 6 will be 0 plus 1. So 0 minus 0 plus 1 ends up being 1. So the limit as x approaches 0 of g of x is 1. So I have f of, replace the limit as x approaches 0 g of x. We found that out to be 1. So I'm going to be evaluating f of 1. And in this case, f of x is x to the 37th power. So to find f of 1, I just substitute the x in x to the 37th with the 1. So it'll be 1 to the 37th power. And that's simply going to end up being 1. So here, the limit as x approaches 0 of 4x to the 8th minus 6x to the 4th plus 1, and that quantity to the 37th power will end up being 1. Okay. So all of this is example 6. I'll take a look at this next example, example 7. And in this case here, we got the limit as x approaches 1 of x plus 9 divided by x plus 4. That quotient is to the 3rd power. And I'm going to evaluate that limit. Okay. And I'm using the fact that I can take the limit as x approaches 1 of f of g of x. That would be the limit as x approaches 1 of, take that back. That should be f of the limit. F of the limit as x approaches 1 of the inside function g of x. But let's identify what f of x is and what g of x is. And of course, it does follow the fact that we're doing f of g of x, where g of x is the inside function. So here, that x plus 9 over x plus 4, that's my inside function, which will be g of x. X plus 9 over x plus 4. Well, if g of x is that x plus 9 over x plus 4, then f of x had to start off as, since this was put in place of x, has to start off as x to the third. So f of x is x to the third. All right. So now let's go ahead and try to take the limit and avoid this yellow line that I have on this paper here. The limit as x approaches 1 of what g of x is. And that's the limit as x approaches 1 of g of x. That's going to be x plus 9 over x plus 4. Well, it may be a rational function, but I'm not going to get a 0 in the denominator when I replace the x with 1. Only time I get a 0 in the denominator is when x is -4. But here I have x equals 1, so I can use direct substitution. So this will be 1 plus 9 in the numerator divided by 1 plus 4 in the denominator. 1 plus 9 is 10 divided by 1 plus 4, which is 5. 10 divided by 5 is 2. So the limit as x approaches 1 of g of x is 2. So I'm going to come over here, bring down the f, and replace this with what the limit as x approaches 1 of g of x is equal to 2. So I'm going to evaluate f of 2. Now f of 2 is x cubed. F of x is equal to x cubed, and x is equal to 2. So let me substitute the x in f of x with 2. So it'd be 2 to the third, or 8. And that would be the final answer there. The limit as x approaches 1 of x plus 9 divided by x plus 4, quantity cubed, is 8. Okay. And here's one more example of this using composite functions here. Let's say I want to determine the limit as x approaches 2 of the square root of 5x plus 2 divided by 4x minus 5. Well, let's identify what f of x is and what g of x is. And we're following the fact that we're dealing with f of g of x, where g of x is the inside function. Well, what's underneath that radical is your inside function. So that 5x plus 2 over 4x minus 5, that would have to be what g of x is. 5x plus 2 divided by 4x minus 5. And since this was put in place of x, that means f of x had to start off as the square root of x. So f of x is the square root of x, g of x is 5x plus 2 divided by 4x minus 5. All right, so now I'm ready to take the limit as x approaches 2 of f of g of x, which is the composite function. That means I can do f of the limit as x approaches 2 of g of x. Well, first of all, let's go ahead and take the limit as x approaches 2 of g of x. Start with that. And my g of x is that 5x plus 2 over 4x minus 5. So Let's replace that, be the limit as x approaches 2 of 5x plus 2 over 4x minus 5. Now, when I substitute the x with 2, I will never get a 0 in the denominator. I'm not going to get 0 in the denominator. Only time that will happen is when x is equal to 5 over 4. But I'm not dealing with 5 over 4 here. I'm dealing with x approaching 2. So let's substitute x with the 2. So here I'm using direct substitution here. Now, keep in mind, when you're dealing with rational functions, direct substitution only works when that limit, the limit where you're taking, then x approaches some value, that value does not give you a 0 in the denominator. So for the numerator, if I do 5 times 2, that will be 10. 10 plus 2 would be 12 over 4 times 2, which is 8. 8 minus 5 will be 3. So now I get 12 over 3, which is 4. So the limit as x approaches 2 of g of x will be 4. So let me come back over here, bring down the f, substitute this with what it's equal to. It'll be 4. So I'm going to be evaluating f of 4. But here, f of x is the square root of x. So there, I would just replace the x with 4. So it'll be the square root of 4, which ends up being 2. So here, the final answer for the limit as x approaches 2 of the square root of 5x plus 2 over 4x minus 5, that ends up being 2. Okay. All right, next we'll look at the intermediate value theorem. Okay, so that's the last thing in this video we'll talk about here. Now, a common problem in mathematics is finding solutions to equations of the form f of x is equal to some L. Before attempting to find values of x satisfying this equation, it is worthwhile to determine whether a solution exists. The existence of solutions is often established using a result known as the intermediate value theorem. Here you're given a function f and a constant L. We assume L lies between f of a and f of b. The intermediate value theorem says that if f is continuous on AB, that's the closed interval AB, then the graph of f must cross the horizontal line y is equal to L at least once, as you can see in this figure right here. Has to cross the line, the horizontal line, y equal L, at least once. Although this theorem is easily illustrated, its proof goes beyond the scope of this text and beyond the scope of this course. And also in this case right here, you can see here's L right here. So there, that graph, cross the graph, has to cross the line y equal L at least once. So here there is at least one number C in the closed interval AB such that f of C is going to be equal to L when L is in between f of A and f of B. So here we're going to be using that intermediate value theorem, which is on the next page of your handout. Suppose f is continuous on the closed interval AB and L is a number strictly between f of A and f of B. Then there exists at least one number C in the open interval AB, satisfying f of C equaling to whatever L is. Okay. Now, the importance of continuity in Theorem 2.16 that was talked about in one of the previous pages, or on this page, is illustrated down here in this figure, where we see a function f that is not continuous on the closed interval AB for the value of L shown in the figure. That means that there is no value in C of C in the open interval AB satisfying f of C equaling to L. And here is that illustration right here, where you have no value of C in the open interval AB such that f of C is equal to L. And this is one of those graphs that is discontinuous, because it does have a break in the graph, as you can see. All right, so these last two examples in this video deal with the use of the intermediate value theorem. As you can see here in example 9, let's say I want to use the intermediate value theorem to show that the following equation has a solution on the given interval. And then part B, use the graphing utility to find all solutions to the equation on the given interval and illustrate your answers with an appropriate graph. Okay, let's start with part A. What we want to do here is show that this equation has a solution on the given interval. And in this case, we got 4x cubed plus x plus 3 equal to 0. And the interval is from -1 to 1. Okay, here's what we need to do here. Using that intermediate value theorem, we're going to find some C such that f of C is equal to L. Now, let's identify this equation. Let's take a look at this right here. That 4x cubed plus x plus 3, that part right there represents f of x. The 0 that you see here after the equal sign, that's the L. That's the limiting value. Okay, so in this case, L is equal to 0. What that means here is this. We're finding some C where f of C has to be equal to 0. Has to be equal to 0. Okay, and my f of x in this case is that 4x cubed plus x plus 3. What I want to find out is that function continuous for all x. Okay, because it has to be continuous in this case on this interval -1 to 1. Well, by looking at this, it is a polynomial function, meaning that any x value that you assign to it, you're always going to get an f of x value for it. So that means this function f of x equaling to 4x cubed plus x plus 3 is continuous on the interval. In fact, it's continuous for every x. So for every x, this function is continuous. All right, next we're going to evaluate your endpoints. Here we're going to evaluate the endpoints, which are -1 to 1. So I'm going to substitute the x in f of x with -1 and substitute the x with +1. So in this case here, let's start with f of -1 and just substitute each x with -1. So it'll be 4 times -1, and that's cube, plus -1, and then plus 3. Well, if I simplify this, a negative to an odd power will be negative. So -1 cubed is -1 times the 4 in front would be -4. Plus a -1, I can write that as -1 plus 3. -4 plus 1 would be -4 minus 1 would be -5. -5 plus 3 will be -2. And now let's evaluate f of 1. And then just replace each x in f of x with the 1. And then simplify. 1 cubed is 1 times 4 will be 4, plus 1 plus 3. Well, 4 plus 1 will be 5. 5 plus 3 is 8. Now notice, for my endpoints, I do get opposite values. Well, values with different signs. One's negative, the other one is positive, which means that there is a 0 in between here. Okay, from -2 to 8, there is a 0 somewhere. So that means -2 is less than 0 and less than 8. Okay, so that means there is a value between -1 and 1 where f of x will give me 0. So I need to find out what that value is where this function gives me 0. And the only way we're going to have to do that is use the graphing calculator, which is what part B is. Use the graphing utility to find all solutions to the equation on the given interval. Okay. So here we're going to have x is equal to what? This is where our graphing calculator comes in. In this case here, I'm going to put this equation in y1, so I'm going to have to press y equal to, and then type in the 4, the x t theta for the x. I'm going to use the hat key for my exponent. The hat key is that upside down V right below the clear button. So it'd be 4x, and that's cube. Use my right arrow key to get out of the exponential part, and then plus x, get the x, plus 3. And then I'm going to go ahead and do zoom 6. And that's what the graph looks like. And of course, I might as well include that L, which is 0. So that's going to be y equals 0. So let me go back to y equal to, leave that equation in, but in y2, I just include 0 and then do the graph. And there you see that graph of y equals 0. Now, what you want to do here is find this point of intersection, which is right here. Here's y equals 0, and here's a graph of 4x cubed plus x plus 3. You want to find out what that point of intersection is, and that would give you your x value. So in this case, let me do second and trace to go to the calculate menu. The one I want to select is the intersect menu. So I'm going to select number 5 because I want to find out where those points intersect. And this is what I'm going to do. I'm going to put my cursor as close as I can to that point of intersection. And then I'm going to press enter once, twice, and then 3 times. Okay. And it would be in this case, negative 0.817. And I'm reading from right here. That's the point of intersection in this case, negative 0.817. Okay. All right. So here we've found the solution to that equation using our graphing utility. And we'll illustrate the answers with an appropriate graph. Now, in the homework, they're going to tell you, they're going to give you a choice of graphs. You just have to select a graph. In fact, let me see if I can try to pull up that problem here, which is similar to the one that I have here. Okay, there it is right there. Okay, so as you can see here, now they also give you the window setting in this case from -2 to 2 in increments of 1 for your x, and then -10 to 10 with increments of 1 for your y. And then from here, you just take a look at the graph that you got on your screen and pick out which one of these fits the one. And the one that I got, and sometimes I'll go ahead and change the window off camera. I think the one that I got right here is choice B. Okay. So choice B would be the best graph for that equation. So that would be answers choice C. Okay. So keep in mind in the homework, you'll just have to pick which one best fits the one that you got on your graphing calculator. And you might have to change the windows if necessary. All right, here's one more of these. Again, we're going to use the intermediate value theorem to show that the following equation has a solution on the given interval. And then use graphing utility to find all solutions to the equation on the given interval, and then illustrate your answers with the appropriate graph. All right, so we got negative x cubed plus 4x squared minus 3x equals 1. And the interval this time is from -1 to 4. From -1 to 4. Okay. Now, in this case here, I'm going to identify the part that's on the left as f of x. And that 1 is, of course, is what L is. And here I'm going to be finding a value of C. So that f of C is equal to L, or f of C has to be equal to 1, because L in this case is going to be equal to 1. So in part A, if we look at the function f of x, that's equal to negative x cubed plus 4x squared minus 3x. In this case, it's a polynomial function. Any x value that you assign to it, you're always going to get an f f of x value for it. So we can say that it is continuous on all x. So that means that this function is continuous on this interval, -1 to 4. Okay. Now let's evaluate the endpoints. From -1 to 4. Evaluate those endpoints from -1 to 4. So I'll evaluate f of 1 by substituting each x with -1. So this will be negative of -1 cubed plus 4 times -1 squared minus 3 times -1. Well, negative to an odd power is negative, so -1 cubed is -1, but I do have that negative sign in front, so that changes to a +1, plus square negative will be positive, so 1 squared will be negative. 1 squared will be 1 times 4 will be 4, minus 3 times -1 would be +3. 1 plus 4 plus 3 ends up being 8. And now for f of 4, here we substitute each x with 4. So it'd be negative, and then 4 cubed plus 4 times 4 squared minus 3 times 4. Well, in this case here, 4 cubed is 64, but the negative makes that 64 negative, plus 4 squared is 16. 16 times the 4 is 64, minus 3 times 4, which is 12. What's -64 plus 64? That's gone. So you're left with -12. Because -64 plus 64 is 0. 0 minus 12 is 12. Well, I have a positive value and a negative value. That would mean that the 1, which is what L is between -12 and 8. So there is a value of x where f of whatever that is will be equal to 1. Okay. Now in part B, we're going to find out what our x values are. Okay. Now to do that, we need to graph this in our graphing utility. So I'm going to go to y equal to. In y1, I'm going to put negative and then x hat key for the, well, let me clear this out first. I'll clear both of these out. Now, let's start over. Negative and then x hat key and then cubed. Right arrow to get out of it. Plus 4x squared plus 4x for the x theta for the x. Hit your x squared key minus 3. And then hit your x t theta for the x. Now in y1, I would normally put 0 in, but I also have to put that L, what L is. In this case, this time is 1. So in y2, I'm putting 1 in. Okay, now let me give you the window for this. Now we're going to go to press the window key. But x min would be from -2 to 5 in increments of 1. Your y min, -6. Y max will be 6. The increment there, the y scale will be 1. Now I'm going to press graph. Now that is what the graph looks like. And there are the 3 points of intersection for y is equal to 1. You have 3 points of intersection. This first one, the second, and the third. So we have 3 points of intersection. So we need to find out what they are. So in this case here, I'm going to start with the one on the far left. And to do that, I'm going to do second and trace and select number 5 for intersection. Now where the blinking cursor is, I'm going to put that cursor using my left and right arrow key. I'm going to use my left arrow key to put the cursor on top of that point of intersection, or as close as I can. And then I'm going to hit enter 1, 2, 3 times. And as you can see, I do have one of my points of intersection. And that's negative 0.24698. But let's say I want to round that off to 3 decimal places. That will end up being negative 0.247. And now to find this second point of intersection, which is this one right here, again, I'll do second and trace for the calculate menu, select number 5. This time I use my right arrow key to put the cursor on top of that other point of intersection, the second point of intersection. And then press enter 1, 2, 3 times. And there will be my other point of intersection here. That would be 1.4450419. Again, the 3 decimal place, that would be 1.445. Okay, so that's the second point of intersection, 1.445. And then finally, for the third point of intersection, which is right here, go to second, trace, select number 5 for intersect. Use your right arrow key to go to the third, put the cursor on that third point of intersection, right there. And then again, press enter 1, 2, 3. This will be 2.802 if we were to round that off to 3 decimal places. So 2.802. Okay, so that's the answer to part B. It's just coming up with the solutions to the equation on that given interval. And they are in that interval between -1 and 4, as you can see. Now, part C, in the homework, you'll be given 4 different graphs to choose from. Because in part C, you're going to illustrate your answer with an appropriate graph. You'll just select the graph that's in MyMathLab that best fits the one that you have on this calculator. So if I go back to this, so here is the one that I was referring to here. So as you can see here, that will have to be answer choice C. Yeah, answer choice C would be this one right here. Okay, because notice where those points are, and notice they didn't put in the graph of y is equal to 1. Okay. All right, so you just choose that as your answer, depending upon what you got in the on your graph utility. Okay, so that will conclude this video on section 2.6, dealing with continuity. Please feel free to contact me if you have any questions about anything that's been presented in this video or anything that's in the homework on MyMathLab.